Hello audience and welcome to our presentation. My name is Martinez.
Yandy. I'm Ramon Orge.
We're the SkySAT team and we're working on the NEE SAT optimization of 3 subsystems. The main objective of this project is to develop 3 new subsystems to put into the 1U picosatellite that has been developed in previous years with the NEE club. Our motivation for this is we're aiming for first place in the FunSat competition. We also want FAU to gain more exposure in the aerospace field. We are very interested in the aerospace industry, and also we want to be able to work in a system that integrates several parts of engineering, not only mechanical but also electrical and computer. The goals are to develop and implement a communication subsystem that's going to allow the satellite to communicate with the ground and vice versa. We also want to optimize, test, and implement an adaptive control subsystem that's going to be able to allow the satellite to stabilize while in space. And we want to increase the power developed by the power subsystem by implementing a new subsystem as well. In order to do this, we had to undergo some literature survey to find more about these picosatellites. We were able to do some research on the several previous launches that have happened and on the schools that have been working on this, different research institutions. California Polytechnic and Stanford were the ones that first did this and developed some standards that we are able to follow in order to make our launch successful. We also looked at the FunSat competition and tried to analyze what they're looking for and the different constraints that we have in order to make, as we said, we're aiming for first place. So we want to make sure that everything is okay. And we looked at the FAU NEE Club previous work on these satellites to try to understand what they've done and what we can optimize with their systems. These are just a list of some of the related standards that we had to look for. It's very similar to the previous teams. We had to look at the NASA ones. And the American Society of Mechanical Engineering ones is ones that we focus when we make all of our designs with mechanical parts.
Well, some of the objectives of this project is to have a fully working prototype that will comply with all the specifications for the FunSat competition. Also to design, test, and implement a communication system for information transmission between the satellite in space and the ground station. This communication system is of vital importance for the mission success. Also to optimize, test, and implement the actuator for the altitude control system, that is the one that will bring the satellite to stabilization once it's launched into space. And the power system, that is the one in charge of generating the needed power for the different components inside the satellite. Due to small size and low cost of manufacturing of this satellite, it will be able to be launched into space with other payloads, sensors, and satellites. Also, will give the opportunity to developing countries to have a high technology device that will gather information, and this information gathered can be used for these developing countries that share common issues to build bridges of cooperation among them. And also the satellite will be pulverized during its entry once its mission is finished, so it will leave no debris on space. Well, basically, as you can see in this diagram, the communication system, all the information gathered from the satellite for the optical camera and the other sensors will be transferred from the Vigo board to the USRP via USB connection, and then from there this information will be converted into a 430 megahertz signal that will be later amplified, will be supplied to watt power in the power amplifier to be transferred to the duplexer. Having a duplexer is very useful in this case because with only one device we can do both transmission and reception at the same time. And then from there to the dipole antenna in the satellite. And from the antenna to the JAG antenna here on the ground station, and then to the duplexer and the USRP. And from here to the computer here on the ground station. This computer is the one that have the LabVIEW software. That is the one that we use to build all the different protocols for the information reception and transmission. In this case, transmission will be commands back to the satellite that will In this case, can help stabilize the satellite or set different parameters in the satellite.
So the attitude control subsystem. The attitude control subsystem is the main part of the satellite. It allows the satellite, once it's launched into orbit, it's going to be tumbling around. And because our objective is to get weather information and take pictures, we want it to be stabilized so that we can get all that right information. So when designing this, there are different options. We could have gone with thrusters or magnet torquers. We chose magnet torquers because thrusters, they have, most of them require fuel, and fuel is something that adds weight to our system, and we want to keep the weight under a certain parameter for the FunSat competition. So and also fuel runs out. So in order for our lifespan, we wanted to be able to have the right amount of energy. So we selected magnet torquers. Magnet torquers, the way they work is we have a ferromagnetic core. It's enveloped in a coil, and then as we pass current through the coil, we create an electromagnet. We put one of these on each axis of the satellite, and then they will interact with the magnetic field of the Earth, and they will create a torque on the satellite. So depending on the current that we put, we're going to be able to stabilize the satellite with each axis. So in order for us to design this, there are several things that we need to look for. We need to look for the magnetic core and its properties. We wanted to have a high ferromagnetic ability. It's the ability for it to be magnetized so that it can produce more torque. We also looked at the wire materials, and we want to find a wire with low resistivity so that more current can be put through it. We have selected so far copper wire, but we're looking at different gauges. And also we want to look at the voltage provided from the power system, because the more voltage we are able to get, the more current we will be able to develop, and more torque will be developed for the system.
We will be implementing a power system that will produce, store, and distribute charge amongst all of the satellite's internal components. We'll be choosing Spectrolab's 29.5% efficient solar cells as the main means of this power conversion. We're going to be placing one 59.65 centimeter squared solar cell on each side face of the CubeSAT, one on the top. We will not be placing one on the bottom, the reason being that's where we have our payload, such as the thermal sensors and the optical cameras. Once these solar cells receive thermal radiation, it's going to convert this radiation into electricity, which will then be stored into a lithium-ion polymer battery regulated by a battery management system. From this storage device, it's then going to be distributed amongst different components such as Beagle boards and Arduinos, which will then in turn power on the subsystems, which is the attitude control system and the communication subsystem, along with the payloads. So where exactly is this energy coming from? When this satellite gets sent up into low Earth orbit, there's going to be two main sources of power. One's coming from the sun in the form of solar radiation, and the other two comes from firstly Earth's albedo, which is the reflectivity of the sun's rays going through the Earth and bouncing back into space, and from the Earth's own infrared radiation. You see the average value for solar radiation, and the other two values for the Earth's power on the screen. The available power is going to be dependent solely on the orientation of the satellite. In our analysis, we found that when any top vertex is pointing directly towards the sun's rays, it will make an equivalent 54.73 degree angle normal to the top face and any two side faces of the CubeSat. Once we have this orientation, we'll be able to harness the maximum amount of power from this satellite. We also did analysis on the minimum amount of power that we'll be able to receive. When one face, specifically the top face, is oriented directly towards the sun, that's when we're going to have the minimum amount of power, in which only one cell is going to have influence from the sun. And when it goes into eclipse, the only form of power that we're going to have available is going to be from the Earth's infrared radiation with the absence of the sun. This is a Gantt chart of our presentation. It's the timeline of the project. As you can see, we're still in the month of April. We're in the design stage. Throughout the summer, we're going to be working on developing, prototyping. After the prototype, we're going to test. We're going to find any room for failure, improvement. And then come the fall, we're going to be selecting the final model and finally present it back to the board in December. So in conclusion, once again, the three subsystems that we will be working on is the communication subsystem, the attitude control system, and a power subsystem. The communication protocols have already been designed. For future work, we'll be connecting all the components and testing them as required parameters. For the attitude control system, core, wire materials, and dimensions, current, and weight has also been analyzed and chosen. For future work, we will now be doing simulations, and testing on these simulations will be performed. And finally, for the power subsystem, we have chosen the solar cells selected already. We have attained the maximum and the minimum amount of powers for this system. And for the future work, we will be developing and testing will also be performed. I'd like to thank you for our presentation, and we leave the floor open to any questions.
Does your system have a 20-year life, like two prior?
Yes. Yes.
Is this magnet torque that's going to keep this correctly aligned? Is it like a seakeeper in boats that they have now? Is it some kind of gyro system or?
Yes, it's going to have several sensors that are going to give us the information that we need to see where we are, and then we send those sensors to the beacon board, and then from there we have the output that is the current. We send it to each magnet torque, and then we're able to stabilize it depending on where we want it to be.
I had a few questions. Could you put up your slide on standards for a minute? Okay. I see the numbers from 0 to 9,000. When you present standards to us, please present the exact standards that you use and only the standards that you're planning to use, because within this standards reference here, I could build anything. Okay, and so when you survey related standards, I really want you to present to us the ones that you need. Okay, so that's first question. You made the statement that the system needed to pulverize itself with no debris left in space on re-entry. Is that truly a requirement? And if so, what are you going to do in order to ensure that you have nothing left when this thing comes through re-entry?
Actually, the satellite will be very small, so once it goes to the atmosphere, it will just burn out. So
yeah, but you've got many different types of materials in there. And some of them are high melting temperature materials. For example, maybe ceramics in some of those electronic devices. Is that going to get burned up in
so
space?
we still have to.
So is that a requirement? Is it really?
No.
Probably not a requirement.
No, it's not a requirement.
So I wouldn't talk about things that weren't requirement. Let me go there. Okay. You talked about simulation. Is it going to be analytical or is it going to be experimental?
Yeah, we're gonna have both of them. We're gonna use ANSYS for the simulation for the magnet torque. We're gonna use ANSYS Maxwell and trying to see how much magnetic field is created by this magnet torque. And then we're gonna also test it experimentally by passing current through it and using a Hall effect sensor to try to actually verify this two data.
Okay, and so my own personal wishes when you present back to us on the experimental side, you set up a designed experiment, you execute the experiment, you get your test data, and then you tell us how it deviates from your analytical prediction. Whether the data is perfect or not isn't as important as the fact that you've gone through the process of actually executing the testing and demonstrated that you got an output. Okay, that's expectation. Thank you.
Any other comments?